Okay, good evening. So a warm welcome to this contact session. Apologies for the delay since we had an issue in setting up the microphone, but we'll get started now. So let me start by answering the questions that have been received till now. And as the discussion progresses, you can also type in your queries in the live chat session, okay? And we would discuss those questions also as appropriate, okay? So yeah, how do I see the list? The live chat. Yeah. Okay, so let's start the questions. Okay. Okay, so let's get started. So I had received a set of questions through that online Excel sheet. So we'll proceed with that list, and then like we will go to the question in the live chat. Questions. Open only one. Okay. Okay. Let's look at one at a time. Okay. So I think one, of course, a bunch of questions were about preparation for the GATE exam. Please note that this is a general course on control systems. Although it is expected that the concepts that you learn would help you in your GATE exam. I cannot readily provide you with any direct suggestions on the GATE exam per se, right? So, but what I can tell you is that like this course will essentially help you in getting a broad overview of what is called as classical control, and also from a practical perspective, it will help you in designing controllers for systems that we can model using transfer functions, okay, as linear time invariant models, okay. So with that background, let me go and address a few questions. So one question is about the first question. Maybe what I will do is that like I will address what is called as a servo mechanism. Like what is typically a servo mechanism and what it constitutes. So in general, the term servo mechanism is used to refer to any system that uses feedback to take corrective action in order to track a desired variable. For example, let us say we have a one-dimensional platform. Let me draw a simple block diagram. See, let's say we have a 1D motion platform, to which I provide a force f of t as an input, and I get an displacement x of t. So in other words, imagine a scenario where you have a 1D positioning table where you need to move an object along the x-axis by providing a force to that table, right? So now let us say I want a desired position xt of t. Okay. In general, if I just give a force input f of t, and that results in the motion of the platform, that is essentially open loop control, right? I can just, if I'm an operator of this machine, I can press a switch to apply a variable force, and then I can essentially regulate its motion. That's open loop control. But on the other hand, you tell me that move the platform by, let's say, a very specific displacement. Let's say you tell me that move the platform by 10 centimeters. So that's my desired, displacement. So what I do is that I measure the actual displacement using a sensor. So then we take the error measure in the displacement, pass it through a controller, okay? And the controller then essentially gives a command to an actuator, which can be, let's say, an electromechanical actuator, let's say a servo motor, which essentially provides the required force through, let's say, a lead screw mechanism, and that essentially moves the platform. Okay, so this entire idea of having feedback to compensate for any potential error between the desired value of a variable and its actual value is essentially constitutes what is called as a servo mechanism. So for example, even if I use the term servo motor, suppose if I want to control the rotational speed of a motor, or let's say the angular displacement of the output shaft of the motor, right? If I have a mechanism by which I use an encoder or let's say a tacho generator to measure the displacement or speed of the output shaft, and then feed it back to a controller so that I get very accurate control of either the shaft, motor shaft displacement or the motor shaft RPM, that's a servo motor, right? So the adjective servo is used in that sense to indicate systems with feedback, okay? So that is one question which was asked. The second question, of course, I am trying to go in a sequence wherein like we follow the same sequence as what we essentially looked at in the class. So this is the first question, and let's say the second question, I would once again reiterate the difference between time variance and time invariance. Okay, so this is also a question that has been posed. So what is the difference between time variance and time invariance? So in general, time invariance is used to represent or to essentially to refer to a system where you provide the same input at different instance of time. You should be able to get the same output, approximately the same output, right? So that is time invariance. So let's take a let's say a very simple example from our day-to-day life. Let me take an alternative example. Let us say all of us are exposed to a car. Either we drive it or we have been in a car. Let's say you are driving a car, and let us say you are driving on the same road at the same speed, straight ahead on a road, right? Now let's say you press the brake pedal by, let's say, a few mm. You expect the car to stop within a certain distance. Sorry. Then let's say you drive the car on the same road tomorrow under the same operating conditions. Then, sorry, no, my throat is bad today. Please excuse me. No? Yeah, I think it's fine. So let's say tomorrow you drive on the same road, and then like you press the brake pedal to the same extent. Then if the car stops in the same distance, then that process of braking is almost like time invariant. On the other hand, if there is a significant difference in the output of the system, in this case, it's the braking stopping distance, right? Then the process is essentially time varying. Okay, so that's what we represent by this curve. Let us say I give, for example, a unit step input at time t equals 0, and as an output, let us say I get a profile which is something like this. Okay, now to the same system, I give an input which is displaced in time. The same input. Okay. Well, let's say I essentially provide it after a time interval of t seconds. Then what should happen is that if the system were time invariant, then the output should also be the same. The only difference being that it should be shifted by the same time interval, capital T. Okay. Then the system is said to be time invariant. Okay. So that's the difference between time variance and time invariance. Okay. Okay. Some questions, like I am going to essentially postpone answering them because we have not yet come to those concepts. See, for example, there have been a few questions on root locus, right? And even like there is a question which is not very clear regarding phase response in Z plane, and even the question on root locus, how to identify an open loop transfer function of unity feedback closed system is in positive root locus or negative root locus. Okay, I request people who send me those questions to send the questions once again with greater clarity. And what I will do is that like we would answer them as and when we progress. If, for example, when we come to root locus, like please raise those questions so that it will be relevant to everybody. Okay, so that's how I'm going to choose what questions to answer today, right? So because I'm looking at what have been the concepts that have been covered till date, and we'll answer questions that are relevant to that set of concepts. Okay, so I am deferring the questions on root locus and even like phase analysis to later sessions. Okay, and another question is about poles. The next question which I will answer is about poles on the imaginary axis. So please note that if you have the S-plane and let's say we have a pair of non-repeating poles on the imaginary axis, okay, at let's say plus or minus j omega. Okay, now if I have a Planck transfer function where all the other poles are in the left-of plane and there is only one pair of non-repeating poles on the imaginary axis, the moment we provide an input which is of the form cos omega t or sin omega t, the output is going to be unbounded in magnitude. Okay, so that's what we essentially looked at. Okay, so that's why some people will refer to as marginal stability, right? So this is something which we discuss. Of course, how do we find out whether there are multiple poles at a location? Like the way you can find in general, like for a polynomial, right? let's say even if I have a polynomial d of s, let me take a very specific example as s plus 1 whole squared times s plus 2, right? We can immediately see that the roots of this polynomial are minus 1, and minus 2. So you can see that the root minus 1 has a multiplicity of 2. Now, we can observe that the value of d of s at both minus 1 and minus 2 is 0, which is unsurprising because that's the definition of a root, right? A root of a polynomial should essentially make the polynomial go to 0, right, at its value, right? Now, if you have a repeating root, right, we can immediately observe that if I take the derivative of this polynomial with respect to s, I'm going to have 2 times s plus 1 times s plus 2, then plus s plus 1 whole square. Okay, so that's what we are going to have. So you see that at s equals minus 1, even the first derivative 0, in addition to the polynomial being 0. Okay, that's one way you can find the multiplicity of a pole in general, right? Because like essentially in general the root of any polynomial, right? So if the multiplicity, if a root has a multiplicity mu, okay, greater than 1, then you will see that the derivative of that polynomial ds, oh sorry, I think let me write it carefully. The the mu minus 1th derivative of that polynomial d of s with respect to s will be equal to 0. So what it means is that d of s will be 0, first derivative will be 0, second derivative will be 0 till the mu minus 1 derivative. Okay, so that's one way to figure out the multiplicity, right? So essentially, yeah. So that's what is how we find multiplicity. And in connection to a set of questions raised on this, I reiterate that if you have non-repeating poles on the imaginary axis with all poles in the left of complex plane, obviously the the input which results in unbounded output are the sinusoids whose frequency is equal to the magnitude of the poles, right? Of course, if the non-repeating pole is the origin, then the step input would give an unbounded output, right? So that's something which we have seen. But please recall that if I have repeating poles on the imaginary axis with all other poles being in the left of complex plane, my output will be unbounded for all bounded inputs. So this is a concept also which we have essentially discussed in our lectures. Okay, so that's something which you should keep in mind. Okay. Now, the next question which I want to answer. Of course, there have been a few questions on the lab videos. You know, like we are in the process of planning those sessions. You know, like so they will come up. Anyway, there will be at least like one hands-on session where we will give you actual real-life data, and you need to design a controller. You know, like that will essentially help you in getting a broad overview of this principles covered in the course. Okay, so that will certainly come up. Okay, but it will take some time. So please bear with us while it's being prepared. Okay, yeah. So then another question was about linear time invariant systems and ODEs. Okay, so please note that in general, the governing equation for the class of systems that we are looking at is a linear ODE with constant coefficient, right? So this is how it comes up. So so if you have an nth order system, the governing ODE that we consider was of this form. You have all terms relating the output on one side and all terms relating the input on another side. Okay. So let me complete writing this. So one can immediately observe that if I have a linear time invariant system, the governing ODE comes out like this, and linearity is reflected in the fact that this equation is linear in y and u, right? So that's how it's one can show that this equation corresponds to a linear system. Time invariance essentially can be attributed to the fact that the constant coefficients of this linear ODE, like turn out to be constants. Okay, one can show that if I have time varying coefficients, I am going to have different outputs irrespective of the fact that I provide the same input at different instance of time. Okay, so that's how time invariance is reflected in this ODE. And causality is reflected, if you recall, by the fact that n is greater than or equal to m. Okay, so in a special case, like even if you have a steady state model or a static model where n is equal to m equals 0, we even have a linear algebraic equation as a model, right? So you see that this governing ODE even will cover linear steady state models or linear static models, okay, of this form. Okay, when we don't have any when we don't not consider any dynamic effects, okay, so we have n equals 0 and m equals 0, and we get a governing equation of this particular form. Okay, so that is a specific case, like as far as this particular class of models is concerned. Okay, and another question is on why origin is considered to be on the imaginary axis. Not really, like, so one can consider, see, origin is anyway at the point of intersection of the imaginary and the real axis. So maybe like there would have been an impression where since we consider the imaginary axis as a boundary of stability and we consider poles at 0 and so on, that might have led to an impression that we consider origin on the imaginary axis. But please note that you can consider it to be on the real axis too, right? Origin is the point of intersection of the real axis and the imaginary axis in the complex plane. Okay, so that's a clarification of that question. Okay, of course, another question is on like whether any practice-based lectures for designing controllers, application of theories and control systems. Yes, some examples will come up during the lecture itself. Like halfway into the course, we will do a case study on gear transmission. That lecture will come up. We'll see how we can essentially use whatever theory we have learned to design, develop a model for a gear transmission, and also like design a controller. Okay, so that part will come up. And as I mentioned, like we are currently undertaking efforts to get the hands-on project also ready. Okay, like that will come up later in the course. Okay, like that hopefully we should be able to get that experimental data live to you. Okay, so that part is something which will certainly come up. Okay, so then I think by and large these are the questions that I received. And as I mentioned, like I am going to defer some questions, like to a later date. Okay, so as far as root locus and phase analysis is concerned. Okay, so now let me go to the live chat. Okay, just questioning this. Okay, I hope everyone is able to look at all the video and also able to hear the audio. Okay, so if you have any questions, like you can type them in. Yeah, if you have any questions, like you can type those questions in now. Okay, so one question is on, I think, Padé approximation, right? So let's look at that. Okay, Padé's approximation. So So this Padé's approximation is also like, I think it's going to come up, right? So in the future lectures. Okay, so I think we would have looked at it when we dealt with first order systems, right? So what happens is that, like in many practical examples, practical situations, we can have delays, right? See, for example, like friction can cause time delay. Like let's say I'm pushing a desk. There's friction at the interface between the desk and the ground. So the moment I give a force to the desk, like I will not get the corresponding displacement. There may be a time delay. Now the question becomes, like how do you account for time delay, right? So let us say I have a term of this form. Okay, so where TD is the time delay. The Padé's approximation provides a way to get what is called as a finite order representation of this time delay. Okay, so if you recall, like what was the the context under which we would have considered it. Like so we would have considered a first order process with time delay. Like to be given by a 3-parameter model, right? So which is of this form, and the transfer function of this process or model, we would have derived it as b by ts plus 1 e power minus tds. Okay, now this e power minus tds is basically has an infinite dimension, right? If you write a power series expansion, you can go to powers of very high powers of s. Okay, but then we want a proper transfer function approximation, right? Isn't it, right? Because when we write the system transfer function, we want numerator and denominator order to be, first of all, finite, and the order of the denominator polynomial should be greater than or equal to the order of the numerator polynomial for the transfer function to be proper and for us to subsequently use the transfer function in analysis. Okay, so for that, what we do is we take this e power minus TDS, right? One way of approximating it is essentially writing it like 1 divided by e power TDS, and then saying that, look, I will expand the denominator e power TDS only till the first power of s. Okay, that's the approximation to one order. Okay, that is one approximation. On the other hand, in the Padé's first order approximation, what we do is we essentially write e power minus TDS as e power minus TDS by 2 divided by e power TDS by 2. You will see that this will effectively result in e power minus TDS. Now what I do is like I approximate both the numerator and the denominator to their first order polynomials. Okay, so 1 minus TDS by 2 and 1 plus TDS by 2. So this will give me an approximate transfer function which is of this form, right? 2 minus TDS by 2 plus TDS. Okay, so this is what is called as the Padé's approximation. Okay, so that is the Padé's first order approximation, right? So we'll see that, like it is quite useful in practice, like and it can be used in multiple practical applications also. Okay, so okay. So there are what to say. There's one question on recommended books. I would prescribe, like I think I mentioned a set of references. Okay, so I would prescribe, like any book from that. Like for example, Control Engineering by Ogata is a good starting point, and so are multiple textbooks. Okay, so I will not recommend any textbook per se, but set of references have already been has already been prescribed to you, right? So you could start learning from Ogata and so on. Okay, so that's something which one can do, right? And just moving on down the screen, like there's one question about dynamic system. Can you explain it more clearly, right? So essentially, let's go here. So what is the concept of a dynamic system? So as far as we are concerned, a dynamic system one. Okay, it may be a process also, to which I provide an input. Okay, and I get an output. Okay, so and here these inputs and outputs are all functions of time. Okay, that's our notion of a dynamic system. So we essentially consider a dynamic system or a dynamic process as one, like wherein we provide an input to the system and we get an output from the system, and the inputs and outputs are all functions of time. Okay, now of course the word dynamic itself comes from the fact that like the the inputs change with time and the output also changes with time. And we also use what are called dynamic models to model dynamic systems. What do we mean by dynamic models? That is models which have derivatives in their equations, like in ordinary differential equations, wherein we essentially use derivatives to capture what can happen in the future, and then use them to model the system. Okay, so that in a nutshell is a visualization or our understanding of what is called as a dynamic system. Okay, so the next question. The next question is how causality can be known from S-plane graph. I think I would need more clarity on that question. If Anand can clarify that question, we'll come back to that. Next question is from Abhishek. Based on transfer function, how we can say that this input result is unbounded, right? So of course, you have to look at the transfer function, right? And we need to look at the poles of the transfer function. See, for example, let us say we have a planned transfer function, as a ratio of two polynomials, right? So now, if you give me an example where, let's say, please note that the boundedness or unboundedness of the output to any bounded input is the result of the poles, right? So let's say, we have a system where I have a pole in the right of plane. Okay, immediately I can say that, I'm going to have unbounded output for all bounded inputs. Okay, so the location of the poles essentially tells me how the system is going to behave when I provide an input to it. Okay, so the moment I have a bounded, a pole in the right of plane, I will have an unbounded output no matter what. Okay. On the other hand, as we just discussed a few minutes ago, if I have non-repeating poles on the imaginary axis, I'm going to have an unbounded output for a particular bounded input, right? Okay. So that's how essentially, based on the transfer function, we can decipher it. Okay. Of course, next question is, what is the problem that we face when poles are to the right of the imaginary axis? Yeah, it's regarding stability, right? So when we have poles to the right of the imaginary axis, so essentially in the S-plane, okay. So let's say we have poles to the right of the imaginary axis, then it means that the system is unstable. Okay, so that is the conclusion we can draw. So what it means is that as far as our notion of stability is concerned, we say that we are looking at bounded input, bounded output stability, right? So the moment we give a bounded input, the output is going to become unbounded. Okay, so that's when that's the problem or the issue that we are going to face when we have poles on the right of plane. Okay, right of the imaginary axis. And in fact, coming back to the question by Anand, right? So I'm just extrapolating from that question, adding my own visualization of the question. So let's say, suppose someone gives me an S-plane construction of this, poles and zeros of a system transfer function. Please note that if I have a planned transfer function, which is a ratio of two polynomials n of s and d of s, typically we say we essentially consider the numerator of order m and denominator of order n. Okay, so please note that for causality, n should be greater than or equal to m. Okay, and immediately you can also see that we are going to have m zeros and n poles. So if you give me an S-plane plot, okay, once again, as I told, I am just having my own interpretation of this question. So suppose if you give me an S-plane plot with poles and zeros of the transfer function, and if there are more poles than zeros, okay, or if there are at least as many poles as zeros, then I would say that the system is causal. Okay, yeah. Okay. So based on transfer function, how can we say? Okay. Now Abhishek's question is that based on transfer function, assuming transfer function is stable, how can we say that this input is going to result in unbounded or violate Bebo criteria? See, the point is, like the moment we say, like the transfer function or the system is stable, like to be more appropriate, I should say the system is stable. That means the transfer function has all poles in the left of complex plane. Okay. The moment, like all the poles of the system transfer function are in the left of complex plane, like you give me any bounded input, the system is always going to give you a bounded output. Okay. So that's the answer to that query. Okay. So if your system is stable and if all the poles are in the left of complex plane, then any bounded input is essentially going to result in a bounded output. Okay. So that is the response to that question by Abhishek. Okay. Of course, thanks a lot for all the positive feedback. We really appreciate it. And maybe, and also towards the end of the session, I will introduce Kesavan and Radhika, who are very important members who have been helping us with the course. They are the teaching assistants for the course. They have been interacting with you on a daily basis. Okay, fine. Okay, the next question from Satyam is that, like, what is the need to study the dominancy of response? Because finally we have to take the value at infinity. Okay, so let me once again interpret this question in my the way I understand it. Okay, the question that is raised is that, let us say you have two systems. Okay, let's say system 1 and system 2. Okay, now the question is, let us say in both systems, see, for example, let us say we consider two fans, right? So I consider fan 1 and fan 2. Okay, so in fan 1 and 2, let us say the steady state value is the same. So what I mean by that, if I switch on both fans, let us say this RPM of the fan, or the rotational speed of the fan, let us say it settles down to 100 RPM in both the systems. But then in system 1, let us say that the response of the fan is like this. Okay, whereas in system 2, the response of the fan is like this. Okay, assuming the same time scale. Obviously, like we can observe that, the first fan is going to be much faster in response, right? So obviously, like the moment I hit the power switch, the first fan is going to respond faster and will go to the final state much faster. Okay, so in any dynamic systems analysis, that's why we are always interested in two aspects. One is what is called as transient response. The second is the steady state response. So both are important. So what you are talking about is steady state response. Yes, although the steady state value is important, the way we reach the steady state value is also equally important. Okay, so that is the reason why we are also looking at dynamic response. Okay, we are worried about how we go to the final value. Okay. So that's why dominancy of response, I'm guessing that you're talking about dominant poles, because the poles which are closest to the imaginary axis will dominate the response characteristics. Okay. I think Satyam, your question is, can you complete the question, because you are saying in case of zeros, like what is the question? How can I calculate the settling time of n% error? Okay, so how do you calculate the settling time of n% error? Okay, so once again, you need to essentially use the expressions. Okay, so for example, let us say you are saying that, look, rather than 2% criteria, let's say, like I want to find settling time for when I reach 90% of the final value. So what you do is that you in your expressions, you just substitute y of t equals 0.9 of the steady state value. Okay, whatever that is, right? And then you can get the corresponding time. So for example, let us say we just to illustrate, let's say the unit step response of a standard first order system, okay, with a gain, we got it to be this. Suppose you are interested in 90% settling time, right? So what you do is that you can substitute y of t to be 0.9 b, okay, and then that will be equal to b times 1, this new settling time by capital T. Okay, so then you solve this and then get the expression for the value for the new settling time. Okay. Okay. So are there any more questions, like based on the ROC in S-plane, is it possible to know causality? What is this region of convergence in S-plane?
Causal system, region of convergence in the left side S-plane. S-convergence is right hand side.
Possible. Okay, I think Anand, I think I will get back to you on this question. Okay, so let me not respond now. So maybe what I will do is that, like, I will get back to you, okay, on this particular question, okay, on applicability of ROC in S-plane to know causality. Okay. So Satyam asks, is there any practical application of unit ramp response of first order system? See, in ramp in general, essentially, ramps are essentially used to construct the input signals, so because in real life, it may be very difficult to construct a perfect step. Okay, so many times, what we may do is that, like, we may end up giving signals like this. Okay, so if I do that, then the ramp response becomes important, okay, to essentially reconstruct the signal and analyze the system response. Okay. And Abhilash asks how to calculate the maximum peak overshoot for fifth undershoot. Okay, so this is where the general expression comes in. I think this is something which you can do. Okay, so for example, when you essentially get the expression for the overshoot, you essentially take the first derivative and equate it to 0, right? And if I recall correctly, I think the peak time will also come as, I think, n pi by omega d. Okay, in general. Okay, please check. Okay, so I'm just recalling from memory. Okay, so you will see that it basically comes as n pi by omega d. Then what you do is that you take the second derivative. Okay, and then of the unit step response of the underdamped second order system, and then you will see that you will get negative value for a maxima and a positive value for a minima. Okay, so essentially what will happen is that, like, if you get a positive value for the second derivative at some of these in time instance, that means that you are having an undershoot. Okay, then obviously you can calculate what is the time required for the fifth undershoot, okay, from this expression. Okay, because you can just keep on increasing the value of n. Okay, but please check it out. Okay, so I will also work it out, but I think you can really use that expression for the unit step response of an underdamped second order system to get this. Okay, yeah. Okay, okay, so I think if there are what is the difference between controller and system? Okay, that is the next question that we are having. Maybe what we will do that we'll continue for another 5 minutes. Okay, so difference between controller and system. Okay, so let's once again revisit our basic feedback diagram. So for us, a system or a plant is an entity to which we give an input u of t and get an output y of t. Now, let us say I want to control the output around a desired value, what we call as a reference input. I measure the output and compare it with the reference input, reference value, and then we pass it through a controller. So this in essence clearly illustrates the difference between our basic system or plant and the controller, right? A system for us, takes an input and gives an output. On the other hand, a controller takes the error between what we desire and what we actually get as its input and gives a control input that needs to be provided to the system as its output. Okay, so the controller decides what input should be provided to the system so that we minimize the difference between the desired output and the actual output from the system. Okay. Okay, so the next question is how dominant poles affect transient response and steady state response. Okay, the dominance of poles is essentially reflected in the way the transient response is affected. Okay, so I'm going to leave you with the homework. So what I want you to do is that consider two systems. Let's say S1, whose plant transfer function is this, and S2, let's say, whose plant transfer function is this. Okay, in both cases, find the unit step response. Okay, I want you to do it as an exercise and then you will get the answer to this question. Okay, you can see that in both these systems, the poles are at -1 and -10. But the pole at -1 dominates the pole at -10. Okay, so that is the definition of a dominant pole. So you will see that you will have a pole at -1 and -10. Okay, so this pole which is closer to the imaginary axis is the dominant pole. Okay, so the dominant pole essentially affects the transient response. Okay, it dominates the transient response. Okay, so what will happen is that you are going to have terms in the output which are going to be exponential functions of the poles, right? You will have e power -t and e power -10t. So you will immediately see that e power -10t goes to 0 very fast compared to e power -t. So the transient response is going to be affected more by the exponential, which has the exponent at -1, which is the e power -t term. So consequently, you can immediately observe that the dominant pole essentially, dominates the dynamic response. Okay, the transient response of the system. Okay. The next question is on why only unit step response are defined. It's see, the point is, by and large, in even from a practical perspective, it makes more. You will see that when you start applying these things to practice, you will see that we can generate step and frequency sinusoids very easily in when we do experiments, right? Steps are to a very good level of approximation. So we typically use step response and frequency response. Please note that we are only not using step response. In this course, we also looked at frequency response, right? So those are two classes of inputs which are very useful for characterizing the class of systems that we are studying. And another perspective is that if you want to define parameters to quantify performance of a system, right, you should always give the same input to the system, right? You should make sure that the input to systems are standard. So that is why we also use the unit step response as a standard input, like which is provided to the system, right? And we analyze the corresponding output. Okay, next question on lump parameter. Lump parameter means, like by and large, what we are doing is that like in general, variables can depend both on space and time. Okay, so when we do lump parameter analysis, what we are essentially referring to is that like we are going to neglect spatial variations, and then like we are going to consider only temporal variations. So that is a lump parameter analysis, right? So that we make variables only as functions of time. And the consequence is that like we have the governing equations to be ordinary differential equations. Okay, so that's lump parameter analysis. Okay, how to conclude dominant and insignificant poles? Yeah, as we discussed, like the dominant poles are the ones, like which what to say, essentially are closest to the imaginary axis, and the less dominant ones are the ones which are farther to the left of the imaginary axis. Okay, so please remember the dominant poles are the ones which are closest to the imaginary axis. Okay, they dominate the transient response, okay, of the system. The next question is, can you explain more about pole zero cancellation and the effect of zero located in the vicinity of the imaginary axis? Okay, so pole zero cancellation is essentially this, right? See, for example, let us say, let me take an example and then like tell you in more detail, like what is pole zero cancellation, and let's say, like when it can create a problem. Let us say, like we have a system, let us say we consider a system, transfer function is 1 by s minus 2. Okay, we immediately see that the system is unstable. Now, like let us say, like I try to do pole zero cancellation. Okay, so let us say, like I propose a mechanism wherein I give a reference input to a block which is like s minus 2 divided by, let's say, s plus 2, and then I give the corresponding output to this plant, and then you get an output, right? Y of s. Now you can immediately see that y of s, I can write it as 1 divided by s minus 2 times u of s, which I can rewrite as 1 divided by s minus 2 times s minus 2 times s by s plus 2 r of s. Okay, mathematically, what we are doing is that we are cancelling this pole at 2 and 0 at 2. Now, the resulting transfer function of this composite system, of this cascaded system, is 1 by s plus 2. And we think we have stabilized the system, but not really, right? What has happened? If we consider the S-plane, in this case, what has happened is that initially I had a pole at 2. Now what we are doing is that we are saying, look, I will place a 0 exactly at 2 and then place another pole at minus 2, making thereby, in a sense, giving the impression that I'm shifting the pole from the the right of plane to the left of plane. But then this is very difficult to achieve in practice. Why? Because due to multiple reasons. Please note that even the entire process of this transfer function based design is an approximation. Okay, we know that, like we have something called a pole at +2, but then it can be at 2 plus or minus epsilon. Okay, it can be in a range around 2. Similarly, the 0 also we are saying that it's around 2. Okay, but the 0 can be at, let's say, 2 plus or minus delta. Okay, around 2. Now, in the case of some unmodeled dynamics, okay, or some approximations that we use in the modeling process, right? The pole's location is only approximate, right? And then what will happen is that in theory, we will never be able to exactly cancel these poles. Okay, so that's why we don't rely upon pole zero cancellations, particularly in the right of complex plane. Now, what happens when we come to imaginary axis? The same logic holds, right? So let's say we have poles close to the imaginary axis, and then I want to cancel these poles using a 0. Same logic applies, right? So when we go closer and closer to imaginary axis, which is the boundary of stability, there may be always some perturbations, parametric variations in the system, which can slightly change the location of these poles. Sometimes, like they may even cross over, right, to the right of plane. Under such situations, if we just use pole zero cancellations, like we are going to be off, right? The pole 0 which we designed is not exactly going to cancel the pole, and then the system may become unstable or erratic, right? So that's something which we want to avoid. Okay. How to calculate a steady state error for non-intuitive feedback systems? I'm not sure whether we have come to steady state analysis yet. We will do it. Okay. So those things are coming up in the future lectures. Okay, as far as steady state feedback is concerned. Okay, where positive feedback system is concerned, like to the best of my knowledge, by and large, we use negative feedback. Okay, but then we also learn about positive feedback in the sense that sometimes, like in the feedback part, there may be some mappings, like which may change the nature of the signal. Okay. So in a sense, like we may need to end up using positive feedback, but by and large, we are going to encounter negative feedback systems in practice. Okay. How can we say if we have 0 in RHP, the output y of t starts in one direction? Okay. That is essentially the consequence of non-minimum phase 0. So once again, I'm going to leave you with the exercise. Oops. Okay, I gave you 2 problems to do. So consider another system. Okay, as a third problem, where you consider a plant transfer function s minus 2 divided by s plus 1 times s plus 1. Okay, please do this and convince yourself. You will see that when you have a pole in the right of plane, the system output will start in one direction and then go to the other direction. Okay. Fine. I think if there are no further questions, like I think we will close this session. Okay. System controllability and observability. Like we will revisit this question once we look at state space representation. Okay. So controllability and observability, like have to do with state space realizations. Okay. But in a nutshell, controllability essentially tells us, like something about, from a very pragmatic perspective, controllability essentially helps us in choosing actuators, whereas observability, like can help us in choosing sensors. Okay. But we will come to this later. Okay. We are going to briefly revisit state space. So my request to Anand is that, like, please raise this question at the appropriate time. Okay, when we look at state space representation. Okay, yeah, fine. I think we will close this session now. Okay, but let me introduce Radhika and Kesavan. Can we go to this video, please? No. How do we go to this video? So I thank all of you for participating. We'll have these interactive sessions at least once every month. Okay. And my question to you is that, like, kindly send these questions in advance. Okay. Once you get the notice, so that like it also gives me time to come prepared with an answer, which will also increase the effectiveness of these sessions. Okay. Okay. So thank you for your participation, and we would meet once again in the next feedback session. Please do all the assignments and get back to us if you have any questions. So let me also introduce Kesavan and Radhika. So Kesavan and Radhika are PhD, pursuing the PhD at IIT Madras, and they are the primary teaching assistants. Okay, this is Kesavan, no, and Radhika. Okay, so of course I thank them for the support. Like I think they have been very invaluable to our team. Okay, and Kesavan and Radhika have been in touch regularly by posting announcements and also responding to your queries. Okay, so please keep watching the videos, and posting queries in the course webpage, and then I look forward to the next interaction. Okay, thank you and have a good day. Okay, thank you. Let's stop.